Okay, let's go over the answer to the application exercise that you all did last class. So I got you this far. I showed you that the expectation of beta hat given x is equal to the expectation of the identity matrix times beta plus x transpose x inverse x transpose epsilon given x. Okay, so we got this far, and so now let's remember what we learned about expectations to try to simplify this expression. So the first thing we'll notice is that we've got this plus here, and if you remember from the rules about expectations, when you're adding two things, even if, regardless of if they're fixed or random, we can split the expectation into kind of two pieces. Basically, we can pull that expected value through. So I'm going to use that first rule here, and I'm going to set this equal to the expectation, and I can just call this beta, because if we multiply beta by the identity matrix, we just get beta. So the expectation of beta plus the expectation of x transpose x inverse x transpose epsilon given x. And actually this should be beta given x. So let's fix that real quick. The expectation of beta given x. Now, this next part I think is a little bit trickier because you have to have a keen understanding of what is fixed, so what's a constant, and what is not, what's random. And so this is where, if we were, when I was going through it in the slides, I had a nice little text box at the top that said, these matrices are constants, these matrices are random. And this time we didn't necessarily have that, so you sort of had to have that intuition. And so I'm going to tell you now which pieces of this are fixed and which are random, and then maybe we can try to sort of build some intuition as to why that's the case. And so the expectation of beta given x, this is just going to be beta, because this is actually here, that's going to be fixed. So beta is fixed, so we can pull that out. And so this is like when you have the expectation of A or the expectation of some matrix that is a constant, it's just that constant. And now here, parts of this expression are random and parts are constant. And so what in here is constant and what is random? Well, we're taking the expectation of some x's, and so this is some function of x's, and then epsilon given x. And so the fact that we have this given x, that basically makes these x's that we're dealing with also constants. And so we can pull those x's out of the expectation and just end up with the expectation of epsilon given x. So this is really important. I noticed a couple of you split this out into the expectation of the x parts times the expectation of epsilon. And that's actually not exactly what you want to do. Often when you have multiplication, you have to be really careful splitting those expectations out if there's not a constant involved. Because the expectation of x times y, where both x and y are random, is not necessarily going to be the expectation of x times the expectation of y. And so you don't want to necessarily pull that expectation through when you're doing multiplication like you can with addition, unless you're dealing with a constant or you have some other situation that we might talk about a little bit more in the future. But in general, you don't want to just pull that through. So that would not be the correct reasoning. The reason why we can pull these out is because they're actually constant, because we're taking this expectation with respect or conditioning on x. So I can pull those out, that x transpose x inverse x transpose. Those come out of the expectation because they're constant, and I'm left with just the expectation of epsilon given x. So I've got now that the expectation of beta hat given x is equal to beta plus x transpose x inverse x transpose times the expectation of epsilon given x. Now what's going on with this little part right here, this expectation of epsilon given x? I think I had given you a rule early on, and this is something that maybe you'll remember from your previous statistics class where you first learned about linear models. But this is basically an assumption, an underlying assumption of linear models is that this is 0. We expect that the expectation of our errors given our data is 0. We want to, and otherwise linear regression, the least squares, it wouldn't hold. So this is a true, just like a true assumption that underlies our model. And so if this expectation is 0, then it's going to cancel out this whole part, because if you multiply 0 by anything, you just end up with 0. And so that leaves us with beta. So there you have it. The expectation of beta hat given x is equal to beta. And now if we actually want to take, so using our lob iterated expectations, or our lob total expectation, we know that the expectation of beta given x is going to be equal to the expectation of beta. And this is the thing that we're interested in, this expectation of beta hat. And so by this rule, we can do this iterated expectation. We know that this inside part we just solved is beta. And so now if I take the expectation with respect to x of beta, that's just going to be equal to beta, because as we mentioned up here, beta is fixed, beta is a constant. And so we can then kind of finally solve that the expectation of beta hat is equal to beta, and thus beta hat is unbiased. And so there you have it.